So, good morning, students. This is Arvind, Assistant Professor, Department of EEE, DBS IT Kavali. So, in the previous classes, I discussed about some concepts of basic concepts of fax controllers, and now I am going to discuss. I am going to start the second chapter, that is voltage source converters and current source converters. So, actually, this chapter contains two parts. First one is voltage source converters, and next one is current source converters. So, firstly, I will start with the voltage source converters. Okay, why I am starting the first part as a voltage source converter means it is the basic need for the fax controllers, and this is the main controller for the fax controllers. So that's why I am starting the voltage source converters. So let us going into the topic, that is, so second chapter name is voltage and current source converters. And next, these are the contents we are going to cover in this chapter. That is, first one is basic concept of voltage source converters, and next one is single phase full wave bridge converter, and third one is three phase full wave bridge converter, and transformer connections for 12 pulse, 24 and 48 pulse operations, and three level voltage source converters, and pulse width modulation converter, and next converter rating. So up to converter rating we have the voltage source converter concept, and next we will go into the part 2, that is the current source converters. In the current source converters, so I am going to start concept of current source converters, and next one is thyristor based converters, and next one is current source converters with turn off devices, and current source versus voltage source converters. That is nothing but difference between current source converters and voltage source converters. These are the contents I am going to cover in this chapter, and firstly I will start with the voltage source converters concept. So let us go into the topic. So first, in the first one is voltage source converters. So the first concept is basic concept of VSC. So VSC is nothing but voltage source converters. You already know this voltage source converter in the previous chapter as a basic definitions. Okay. So I am going to start this one, basic concept of VSC. So here, actually, you know that the voltage source converter is the building block of STATCOM, SSC, UPFC, IPFC, and some other controllers. You already know why, because in the previous chapter I discussed one topic, that is basic definitions of fax controllers. In that one we are discussed about different types of fax controllers. So in that one I discussed about voltage source converter and variable impedance type. So in the voltage source converters we have the STATCOM, SSC, UPFC, and IPFC. So actually this is the building block of STATCOM, SSC, UPFC, IPFC. So here STATCOM is a shunt connected controller, SSC is a series connected controller, and UPFC, IPFC, these are all in the combined series and shunt controllers. Okay. So here the voltage source converter is the building block of STATCOM, SSC, UPFC, IPFC, and some other controllers. Okay. So then these are so-called conventional thyristor device has only the turn-on control, the so-called conventional thyristor device. So if you use the thyristor as a control device or conventional control device for the system, so it has only the turn-on control. So if you want, so its turn-off control depends on the current coming to zero as per circuit and system conditions. So up to now we are using the conventional thyristor device with turn-on control, only the turn-on control. So if the particular thyristor device, conventional thyristor device is turn off, so it will depend upon the current coming to zero, as per circuit and system conditions. At that time the conventional thyristor device is in the turn off condition. Okay. So here we are using different devices. Okay, so those are devices such as GTO. So what is the GTO? The abbreviation of GTO is gate turn off thyristor. GTO, gate turn off thyristor. And next one we have IGBT. So IGBT is integrated gate bipolar transistor. Integrated gate bipolar transistor. And MTO, that is the MOS turn off thyristor. MOS, MOS turn off thyristor, that is metal oxide semiconductor. MOS means metal oxide semiconductor turn off thyristor, MTO. And next one is IGCT. So IGCT is a integrated gate commutated thyristors. IGCT is the integrated gate commutated thyristors. Okay. So and similar devices have turn on and turn off capability. So what So up to now I discussed some devices. So these devices have the turn on and turn off capability, both turn on and turn off capability. Okay. So these devices are more expensive. So I discussed GTO and next IGBT, IGCT and MTO, IGCT. So these are all devices are more expensive and have higher losses than the thyristors without turn off capability. Okay, than the thyristors without turn off capability. Okay, so that's why, however, turn off devices enable converter concepts. Okay, however, turn off devices enable converter concepts, so that can have significant overall system cost and performance advantages. Okay, however, turn off devices enable converter concepts, so that can have significant overall system cost and performance advantages. So those advantages are, so these advantages in principle result from the converters. So these advantages in principle result from the converters. So which are self-commutating. So actually we have two types of converters. One is self-commutating converter and another one is line-commutating converters. So based on these, so these disadvantages in principle result from the converters which are self-commutating as against the line-commutating converters. Okay. So here we have different one. So here, so compare to the self-commutating converter. So compare to the self-commutating converter, the line-commutating converter must have an AC source, connected to the converter. Okay, why? Because it consumes reactive power and suffers from occasional commutation failures in the inverter mode of operation. We have two modes of operation. One is rectifier mode of operation and another one is inverter mode of operation. Here, compared to the self-commutating converter, the line-commutating converter must have an AC source connected to the converter. Why? Because it consumes reactive power and suffers from occasional commutation failures in the inverter mode of operation. So therefore, unless a converter is required, so here a converter is required to function in the two lagging currents only. Two lagging currents only. So that means two lagging currents only. That means consuming reactive power while converting active power. Okay, therefore, unless a converter is required to function in the two lagging currents only. So here two lagging currents, why the function of the two lagging currents is the consuming the reactive power while converting active power. Okay, consuming reactive power while converting active power. Okay, so here converters applicable to FACTS controllers would be self-commutating type. So here we are using the self-commutating converters in the FACTS controllers. Why? Because converters applicable to FACTS controllers would be self-commutating type. Self-commutating type. Next. So actually there are two basic categories of self-commutating converters. So our main concept is voltage source converter and current source converters. So these two basic categories of self-commutating, we have the self-commutating converters, two basic categories. Those are VSC and CSC. So voltage source converter and current source converter. These are the two basic categories of self-commutating converters. Okay. So firstly we will look into current source converters. So here current source converters in which direct current always has one polarity. So current source converters contains direct current, that is DC current. It always has one polarity. Okay, and the power reversal takes place through reversal of DC voltage polarity. Okay, current source converters in which DC current always has one polarity and the power reversal takes place through reversal of DC voltage polarity. And next one is voltage source converter. So here the voltage source converter in which the DC voltage always has one polarity. So in the previous, that is the current source converters in which direct current always has one polarity, but in the voltage source converters the DC voltage always has one polarity. Okay, and the power reversal takes place through reversal of DC current polarity in the voltage source converter, but in the current source converter the power reversal takes place through reversal of DC voltage polarity. So these are the current source converters and voltage converters functionalities. Okay. So next. So actually the conventional thyristor-based converters. So the conventional thyristor-based converters being without turn-off capability. So can only be current source converters. So without turn off capability can only be current source converters, whereas turn off devices based converters can be of either type. So here the current source converters are of without turn off capability. So remaining one, that is the voltage source converters, or anything or any other devices. So whereas turn off device based converters can be of either type. Okay. Next, for reasons of economics and performance, voltage source converters are often preferred over current source converters for fax applications. So this is the reason why we are prefer voltage source converter over current source converters means we are based on economics and performance. Voltage source converters are often preferred over current source converters for fax applications. Okay, next, since the direct current in a voltage source converter, so already you know that since the direct current in a voltage source converter flows in either direction, so you already know this point. So since the direct current in a voltage source converter flows in either direction, the converter valve have to be bidirectional. The converter valves have to be bidirectional, and also since the DC voltage does not reverse, why? Because the converter valves have to be bidirectional. Okay, next we are going to the main concept. Okay, so from this concept onwards we are going into the main concepts in the second chapter. Okay, so here the turn off devices need not have reverse voltage capability. So the turn off devices need not have reverse voltage capability. Such turn off devices are known as asymmetric turn off devices. So note this point, the turn off devices need not have reverse voltage capability. Such turn off devices are known as asymmetric turn off devices. Okay, here I am taking the voltage source converter. So if you observe this diagram, we have one thyristor, one turn off device, that is thyristor, and next one we have parallel connection diode. Okay, so if you observe this diagram here, a voltage source converter valve is made up of an asymmetric turn off device. Here we are using the asymmetric turn off device. So I already said that what is meant by asymmetric turn off device? The turn off devices need not have reverse voltage capability. So such turn off devices are known as asymmetric turn off devices. So here I am using the asymmetric turn off device such as GTO. So this turn off device is called as a GTO here. So with a parallel diode connected in reverse. With a parallel diode connected in reverse. If you observe this diagram, you will understand. You can understand. Okay. So here I am using asymmetric turn off device. The name is GTO and with a parallel diode connected in reverse. So if you see this diagram, you can understand. Okay. And next, so actually in general, the symbol of one turn off device with one parallel diode. So already I showed in this case. Okay, in general, the symbol of one turn off device with one parallel diode. You already, if you observe this diagram, you understand. So here I am taking one turn off device, this one GTO, and next with one parallel diode, this one. Okay, so will represent a valve of appropriate voltage and current rating required for the converter. Okay, this will represent a valve of appropriate voltage and current rating required for the converter. Okay, so actually, so within the category of voltage source converters, okay, within the category of voltage source converters, there are also a wide variety of converter concepts. So not only these, we have so many a variety of converter concepts. The one relevant to the fax controllers are this one only. So the one relevant to the fax controllers are this voltage source converter and current source converters. Okay, there are some converter topologies that are suitable for supplying and consuming reactive power only and not for converting active power. Okay, they are not discussed in this chapter. We will discuss only voltage source converters and current source converters, that too the reactive power, consuming reactive power. Okay, and next I will show one diagram. Okay, the diagram describes the basic functioning of voltage source converter. Basic functioning of voltage source converters. So this one. So observe this diagram. So this is the basic functioning of voltage source converter diagram. So please observe this diagram carefully. I will explain the operation of voltage source converters or basic functioning of voltage source converter by using this diagram. Okay. So carefully observe this one. So here the diagram shows the basic functioning of a voltage source converter. So here the internal topology of converter valves is represented as a box. So this box contains converter valves. This box contains converter valves. So here we have one thyristor and it is connected to the parallel of the diode, parallel to the diode. Okay. So the internal topology of converter valves is represented as a box with a valve symbol inside. Okay. Next, on the DC side, if you observe the left side of the diagram, we have the DC side. Okay. So on the DC side, voltage is unipolar. So if you see this diagram, on the DC side, we have the VD. We have VD, that is the active DC voltage. Okay, DC side voltage. So this will contain only unipolar. Okay, unipolar direction. Okay, on the DC side, voltage is unipolar and is supported by capacitor. So if you observe the left hand side of this diagram, you will have one capacitor. So the voltage is unipolar and is supported by a capacitor. Okay. So this capacitor is large enough. Why? Because to at least handle a sustained charge or discharge current. So this capacitor is large enough to at least handle a sustained charge or discharge current. Okay. That accompanies the switching sequence of the converter valves and shifts in phase angle of the switching valves without significant change in the DC voltage. So for that purpose we are using this DC capacitor. So this capacitor is large enough, I already said that. Why? Because to at least handle a sustained charge or discharge current. Okay, that accompanies the switching sequence of the converter valves and shifts in phase angle of the switching valves without significant change in the DC voltage. Okay, so that's why the DC capacitor voltage will be assumed constant. Okay, why? Because here without significant change in the DC voltage. So there is no change in the DC voltage. That means the DC capacitor voltage will be assumed constant. That means VD is constant. Okay, DC side voltage is constant. That is VD is assumed to be constant. Okay, and also, so it is shown on the DC. It is shown on the DC side that the DC current can flow in either direction. So if you observe the left hand side, the ID, that is the DC current. So this DC current will flow in either direction. Okay, in either direction. So voltage is a unipolar direction, but current is a either direction. Current flow in either direction. Okay, and that it can exchange DC power with the connected DC system in either direction. Okay, and that it can exchange DC power with the connected DC system in the either direction. So this one, active DC power diagram. So active DC power indicated here. So this will also contains in either direction. Okay, and next, so this is for the DC side explanation, and coming to AC side. So observe in this diagram the right side. Here we have the AC side. Okay, I will explain this one. So shown on the AC side is the generated AC voltage. The generated AC voltage connected to the AC system via an inductor. So here AC side is the generated AC voltage. AC side is the generated AC voltage. This one VA. Okay, VA is connected to the AC system via an inductor. It is connected to the AC system via an inductor or reactor. Okay, inductor or reactor. So being an AC voltage source with low internal impedance, a series inductive interface with the AC system, is essential. Why? Because to ensure that the DC capacitor is not short circuited and discharged rapidly into a capacitive load such as a transmission line. Okay. So here we are using the low internal impedance for the voltage source here I am using the series inductor interface with the AC system. That means usually through a series inductor or a transformer. So is essential. Why? Because it is essential to ensure that the DC capacitor is not short circuited and discharged rapidly into a capacitive load such as a transmission line. Okay, such as a transmission line. Also, an AC filter may be necessary, but it is not shown here. AC filter, but it may be necessary. Okay, it may be necessary, not compulsory. Okay, also an AC filter may be necessary following the series inductive interface, to limit the consequent current harmonics entering the system side. Okay, why we are using the AC filter means in the series inductive interface to limit the consequent current harmonics entering the system side. Okay, for that one we may be necessary by using the AC filter. Okay, so actually basically a voltage source converter generates AC voltage. Okay, basically a voltage source converter generates AC voltage from a DC voltage. So it is for historical reasons often referred to as an inverter. Okay, for historical reasons often referred to as an inverter, even though it has the capability to transfer power in either direction. So I already said that it transfers power in either direction. Okay, with a voltage source converter, the magnitude, the phase angle and the frequency of the output voltage can be controlled. Okay, with a voltage source converter, the magnitude, the phase angle and the frequency of the output voltage can be controlled. Okay, so we have another diagram. This one. So this is for a single valve operation. So why we are going into the single valve operation means, so here in order to further explain the principles, we are using this single valve operation. So carefully observe this diagram also. I will explain this diagram in detail. So here the figure shows a diagram of a single valve operation. You already know that. So here the DC voltage, that is VD on the left hand side. Okay. So DC voltage VD is assumed to be constant. So in the previous case also we assumed the DC voltage constant. Okay, and supported by a large capacitor. In the previous case also the DC voltage is supported by a capacitor, large capacitor. So that too with the positive polarity side is connected to the anode side of the turn-off device. So this is the turn-off device. Okay, thyristor. So this one is a thyristor. This is the turn-off device. So here the positive polarity side connected to the anode side of the turn-off device. Okay, so that means when the turn-off device 1 is turned on, that is thyristor 1. Okay, thyristor. So when the turn-off device 1 is turned on, the positive DC terminal is connected to the AC terminal. The positive DC terminal is connected to the AC terminal A. So I indicated A point here. After connecting the converter valves, I am indicating the AC side A. Here we have the AC voltage and AC current and an inductor, okay, or reactor. So observe carefully. So when the turn-off device, that is the thyristor, not diode, thyristor. When the thyristor turn-off device 1 is turned on, the positive DC terminal is connected to the AC terminal A, and the AC voltage would jump to VD, would jump to plus VD. Okay, positive direction of VD. Okay. At the same time, if the current happens to flow from plus VD to A, so in this direction, plus VD to A, if the current happens to flow from plus VD to A, that is from through device 1. So this one, through device thyristor. So through device 1, the power would flow from the DC side to AC side. The power will flow from DC side to AC side. Okay. So that is nothing but an inverter action. The power flows from DC side to AC side. That is nothing but inverter. What is the functionality of inverter? It converts DC to AC. So here also the power would flow from the AC side, DC side to the AC side. Okay, through diode 1. Okay, sorry, AC side. That's it. Next, however, if the current happens to flow from, if the current happens to flow from A2 plus VD, A2 plus VD, so it will flow through diode 1. So if the current happens to flow from A.2 plus VD through the diode, through the device, the diode, okay, even if the device 1 is so called turned on, okay, even if the device 1 is so called turned on, and the power would flow from the AC side to the DC side. In the previous case, in the inverter operation, the DC power DC power is converted to AC side, okay, and here the AC power is converted into DC side. Okay, that is nothing but rectifier action. Okay, thus a valve with a combination of turn-off device. Okay, thus a valve with a combination of turn-off device and diode can handle power flow. Okay, can handle power flow in either direction. Okay, can handle the power flow in either direction with the turn-off device handling inverter operation. With the turn-off device having the inverter operation. Inverter action and the diode handling rectifier operation. So please note these points. Okay, so here the turn off device handle, okay, the turn off device handle which operation? Inverter operation, and the diode handling rectifier operation. Okay, this valve combination and its capability to act as a rectifier or as an inverter with the instantaneous current flow in positive or negative direction. Okay, so this valve combination, that is combination of thyristor and a diode, okay, and its capability to act as a rectifier or as an inverter, both, okay, with instantaneous current flow in a positive, that is AC to DC side. Positive means AC to DC side or negative direction respectively. So he is basic to the voltage source converter concepts. He is basic to the voltage source converter concepts. Okay.